Hey there. We're going to do a video here to talk about like a proof of something that's going to be important to us. It's going to make our lives easier. So this isn't a video to show you something brand new that's like you're going to be doing all the time. This is instead a way to sort of get you to realize why a little like quote-unquote trick we might do in class is actually totally okay to do. So we're going to be doing optimization, and we're going to be doing optimization that will involve sometimes some things that could end up as square roots, and we're going to find out why we don't need to make them square roots, because we recognize this interesting little fun fact. So we're starting with this idea, which is that we have a function f. It is continuous, and it has a local maximum at x equals c. I could have started this out saying it was a local minimum, and what we're about to do basically all works as well. I just thought I'll just make it a local maximum. So notes that we could repeat this whole process stating that it's a local minimum, and we can conclude the same thing at the end. Okay, so let's sort of decode this and figure out what does this tell us. So if it has a local maximum at x equals c, then we know two fun things. We know that f prime of c equals 0, or f prime of c is undefined. That's fun fact number one, okay? Because that's where we can switch. That's where our critical points are, okay? And then fun fact number two, f prime changes from positive to negative at x equals c. So if this is the graph of f prime being positive means it's increasing, and then f prime being negative means f is decreasing, so it's changing there. And then this particular example here, f prime is equal to 0 at c, but we could sort of make like a cusp or something like that to show that it could also be undefined there. So what we're going to do now is we are going to actually consider the function y equals the square of f of x. And we want to know what's going on with this function at c. Is it that's like it's also having some sort of local maximum or local minimum at point c, or is it that we can't conclude anything? What we're going to conclude is that actually it does have either a local maximum or a local minimum at c. So like just by squaring it doesn't mean it doesn't have a fun critical point there. So that's our ultimate goal here. So if we're going to do that, so we want to figure out where does this thing have local maxes and mins, we are going to take the derivative of it. So y prime, and I'm going to use the power rule, so 2 times f of x, and then the chain rule, because f is a function of x, and so times the derivative of the inside function we got going on there. Okay, so in our usual maneuvers, when we want to figure out local maxes and mins, we say, all right, so where is y prime equal to 0, or where is y prime undefined? So those are sort of the two ideas. So here we're going to figure out when is 2 f of x, f prime of x equal to 0. Well, that's either at where f of x equals 0, or where f prime of x equals 0. And then we could do the same thing over here, like we just would want to know when is f of x undefined, or f prime of x is undefined. Those would be the two places we would look. 2 is not undefined, so we wouldn't look there. All right. So note that we have these two statements here which match up with one of our thoughts up here. So c has to come out of either here or here. It really doesn't matter which one we choose. Again, like we could do this whole proof again. For the sake of just making life as easy as possible, like let's say it's from here that we find out like, oh, c is where this is. So we're going to go with like f prime of c is actually 0, but it's also possible maybe it was undefined, and we could do the same work but that's not really super necessary. And like, let's say that also other things come out, like we get like it's the function is at a is where it has a 0. Let's say from here we get x equals b, and let's say from here like x equals d. I don't know, I'm just throwing down some random letters here, but let's just say like these are all the different critical points, critical values for this function. All right, so then at this point we usually do some sign analysis. So let's go ahead and do that now. So we've got, negative infinity to a to b, b to c, c to d, d to infinity. Those are all the different, let's say, intervals that we were interested in. And then we want to do sign analysis on f prime, or on y prime, I should say, sorry. And so that's 2 is our first factor. F is our second factor. F prime is our third factor. And then all of this builds y prime for this. So I was really only concerned about what's going on around C. So like I really don't actually care about these values or these values. I'm concerned about these values here, like what's happening when we approach C from the left and from the right. So let's start with the easy thing here. 2 is always positive, so positive, positive. And then we actually do know here, f prime, as we get from C to the left to the right, well, that's fun fact number 2 up here we noted. It changes from a positive to a negative. We know that for a fact. Okay, so now we need to talk about, well, what is f doing at C? So is f changing signs, or does it keep its sign? Because that really matters here. Like if we're going to go positive times a positive times a positive, great. But if it's a positive times a negative times a positive, like we can end up with different values down here. And so it's possible that maybe y prime doesn't change values, or it does. I've already spoiled this. Y prime should be changing values here. It should either go from positive to negative or negative to positive. So that must mean that y prime is keeping its sign. But I want to sort of talk about why it's keeping its sign. So let's go on a little sort of counterexample thing here. So we're going to zoom down here to the bottom of the page, and we're going to go assume f changes signs at x equals c from, let's go with from positive to negative. Okay, so that must mean that f prime of c equals 0. And we're going to keep all the same facts as above. So we know also that f prime of c equals 0. And we know that f prime changes from positive to negative at C. We know that to be true still, okay? So we're going to go with all the same things we've been declaring here. So that means that we're trying to think about a function, f, that has a local maximum that is at an x-intercept in which it changes signs. So let's try to draw this and see what our brains tell us. So here it is. Boom, there's C. I know it's a local maximum, so it's got to be like this, right? But then this statement is saying that, no, wait, it should have changed from being a positive to a negative. So it's above the x-axis when we're less than C, but below the x-axis when we're greater than C. But if that's true, that means that at C, the function is only decreasing, which wouldn't work if also at C we wanted to have a local maximum. So what this concludes is our assumption's wrong. So f does not change signs at C. We could do the same thing if we wanted to assume that maybe f went from negative to positive, but that would then imply that at C, f should be increasing. And again, that's not happening. F is either doing nothing there or sorry, f prime is either doing nothing there or undefined. So an assumption like this, that f could be changing signs when f prime is also changing signs, just doesn't work. You could try all day long, but it's not going to work out. Okay, so what does this mean? This must mean that, coming back up here to our table, our sign analysis, that here, there's no way that whatever goes into this box is either going to be opposite signs of each other. So either it is a plus, meaning f is staying positive the whole time, which would be sort of like in this case. Here's a graph of f, it's got positive values. Or on the flip side of this, it could be that it goes negative, negative, which would just mean like your maximum occurs below the x-axis down here. Well, let's see. So if it doesn't change signs, then if it's the positive route here, positive times a positive times a positive, that must mean that y prime is positive. And then if it's positive times a positive times a negative, that must mean that it's a negative. So in this particular case, y prime has a local maximum. Okay, the other scenario though was, what if f took on negative values there? Well, then it would actually be the opposite here. It would go from being negative to positive, which actually means that this function is taking on a local minimum there. To remind us, the function we're thinking about is the square of f. So here is the ultimate sort of idea behind this. If f has a local maximum or a local minimum at some value, f squared will have some sort of local extreme value at that same number too. So this does not mean, though, that they will be the same type of extreme value. So if it was a maximum for f, it's also possible it could have been a minimum for f prime or f squared. But the fun fact here is that, like, hey, if I can figure out that there is some sort of local maximum or minimum, then I can actually take this value and come back up to my original function of f and go, so what is it? Is it a maximum or is it a minimum? And oftentimes it'll be clear from the context, because we're doing optimization, so there's going to be lots of context. And so it'll say, like, when is something the furthest away, in which case you're thinking of a maximum. So we're going to use this because if we're thinking about like distances, that's like Pythagorean theorem, but like you could come up with that with like a square rooty thing. So let me explain where we're going to use this in a moment, or in class. So like if we're thinking about like, oh, I want to know how far away two things are from each other, and when that's the greatest, you might go something along the lines of like, okay, I'll just set this all up. We got x squared plus y squared equals z squared. I want to know when is z the biggest. So you might solve for z, and then the next step is, let's take the derivative of that. And z prime now equals, and then, ooh, this is not as beautiful as maybe I would have liked it. It's doable, just not fun. So what that proof just told us is that, hey, like doing this is not super necessary, actually. What you can do is come back up to your original thing and say like, I don't know, like f of x is equal to z squared. And so now I'm just going to go ahead and say like, all right, so f of x equals x squared plus y squared. And now I'll take the derivative of this and move forward. Note that taking the derivative of this is going to be a little bit easier. This was maybe poor choice. I probably should have done like, I don't know, something constant. Anyways, so that's the big idea here, is like instead of trying to find the derivative of this and messing around with it, we're actually going to just keep it in our prettiest form here, take the derivative, and whatever numbers we get, we're not going to then plug back into here because that just tells us the squared values. Instead, what we're going to do is plug it in back over to here to figure out the values that we actually want, which is z. All right, well, thank you for joining me. Please take the Google form quiz that is also posted here. As a reminder, it is worth 1 point to answer both questions in the quiz. If you don't get that point and you can't make it up, so make sure that you're doing this in a timely manner. Thank you, and see you on Monday.